So this video lets us take a look at some of the mole stoichiometry that is required when you've got balanced equations. And I know it seems kind of trivial considering how much mole work you guys did in first year, but can't hurt to review. So we haven't looked at mole ratios yet, so we're going to start there, start at the basics. So remember that in a balanced chemical equation, the coefficients will provide a bunch of mole ratios, which is essentially a recipe. Lets you see what proportions things are going to react in. So for example, you've got this reaction of sodium phosphate with calcium nitrate, producing sodium nitrate and calcium phosphate. Notice the coefficients are showing you how much of each is involved. Mole ratios would include things like 2 moles of sodium phosphate to a typo that should be 3 moles of calcium nitrate. Or you can compare a reactant to a product, or you can compare two products. So it doesn't matter where the substances are, mole ratios are going to apply no matter what. So I like to compare the mole ratio to like the switching station in a train yard. You guys ever play with trains when you were little? This thing is the switching station. When a train gets on this switching station, it can rotate, the station itself rotates and lets the train go down any number of tracks. It's kind of what a mole ratio is. A mole ratio lets you get from any unit of substance A to any unit of substance B through that mole ratio. So for example, you can get to molecules, you can get to mass, you can get to concentration, volume, energy, and something you didn't learn last year, electric current. Simply because I needed 6 to make this look nice and symmetrical. So how do you get from moles to molecules or molecules to moles? Avogadro's number, 6.02 times 10 to the 23rd. How do you get from mass to moles? Hopefully you know this one, molar mass. Concentration, most commonly we're going to use molarity. Volume, and I was thinking volume of a gas, so that would be the ideal gas law, PV equals nRT. But you could also get to volume via a density problem. All right, energy, enthalpy of reaction, the delta H, and electric current, something that you will learn later in the year, something called the Nernst equation. I know that's very funny sounding. All right, so example, we've got 21 grams of sodium phosphate and excess calcium nitrate. How much calcium phosphate can we actually make? Well, we're starting with grams. We got to get to moles. Then we can use our mole ratio. Then we're going back to using molar mass to get back to grams. So this guy is our mole ratio. You are going to see it in almost every mole problem that is out there. Whether you use a molar mass depends upon what the units are that you're starting with. Likewise, whether or not you use molar mass here depends upon the units that you're trying to get to. This is a gram to gram problem, so I'm using 2 molar masses. If this were a gram to volume of a gas problem, I'd use PV equals nRT at some point along here. So we'll get to practice all that stuff. We're going to keep it simple right now and just do gram to gram stuff. All right, so one of the applications of doing all this stoichiometry stuff is solving limiting reactant problems. AP loves to put limiting reactant type stuff in there. So if you remember, most of what we do, you've got one reactant and then they don't mention anything else, and so it's easy. But what if they provide you with more than one quantity of reactant? Now you got to figure out what's limiting, and then the limiting reactant is going to control everything else. So typically, if you're given a limiting reactant problem, you've got several questions you're going to have to answer. First and foremost, what's limiting? Therefore, what's in excess? How much product is actually possible? And finally, concerning the reactant or reactants in excess, how much got used and how much got wasted or didn't get used. So, given this problem, 20 grams of ammonia, 120 grams of copper oxide, how much copper can I make? How much of the reactant in excess got actually wasted? So in this case, I'm given quantities of both of the reactants, and I got to figure out something about the copper product. Okay, just because I'm starting with 20 grams of ammonia and more 120 grams of copper 2 oxide doesn't mean that ammonia is the limiting reactant. You've got to figure it out because you got molar masses to deal with and you've got the mole ratio to deal with. 3 versus 2 moles of copper oxide compared to ammonia. So 2 ways to answer what's limiting, 2 common ways to answer what's limiting. Solution A would be to convert grams of one reactant to grams of another and compare that to what you need. So 20 grams of ammonia will react with 140 grams of the copper oxide. If you remember, we were given 120 grams. So in order to use all of the ammonia, we need more than what we have of copper oxide. So we need more than we have, which means copper oxide is going to run out, and ammonia is the reactant in excess. And that's what that idea says right there. The other way that you can do it is to start with each of the reactants that you're given and go to the product. In this case, we want to go to copper because that's the question asks about how much product you can make, how much copper. And then whichever reactant produces the smallest amount, that's going to be limiting. So here I've got to do 2 mole problems. Starting material of 20 grams of ammonia or 120 grams of copper oxide, figuring out how much product I can make. Now, if you notice, I actually have answered my second question by doing it this way. Once I know what's limiting, and since copper oxide produces the smaller amount of copper, copper oxide is limiting, so both solution A and solution B have supported the same result. But I've also found how much copper I can actually make, 95 grams. All my copper oxide runs out, I get 95 grams of copper. Ammonia, I have more ammonia. I could make 111 grams of copper, but that number is artificial because I can only make 95 grams with the copper oxide. So I actually answered the next question by doing the method this way. And there's, again, the rationale that we've talked about. So how much product can I make? Depending upon how you answer the question, you may already have that answer, or how you solve the first problem, you may already have that answer. 95.86 grams of copper oxide is possible because of the calculation that we did right here. Now, if you didn't do it this way, if you did it by going from comparing need to have from one reactant to the other, you're going to have to do a second mole problem because you have to use the limiting reactant that you found in order to get the product. Oops. But either way, you're going to come up with the mass of copper. Finally, how much of the reactant in excess was used? Once again, depending upon how you solve the question, you may already have that answer. If you think back to solution A, if you guessed properly, you already figured out how much of the reactant in excess was used. We, unfortunately, did not guess correctly. We found that ammonia was in excess, so of the 20 grams of ammonia, how much got used? We don't have any information about that yet. So we've got to do a mole problem. So I know all the copper oxide is going to react. How much of ammonia will react with it? Turns out 17.13 grams. So not too bad, not a huge waste. How much did I waste? I'm going to subtract. And I've only wasted 2.83 grams of ammonia. So that's not horrible. But that's how you do all 3 steps. So this PowerPoint is going to be accessible to you guys without the video. So if you need to go back and look at this, you can. But remember that your book has good examples as well. And hopefully you remember them from first year for the most part. All right, another kind of question that you're going to see, theoretical and experimental yields. So the experimental yield, if you remember, is the amount of material you get by actually doing the chemistry in the lab. So data is what's going to give you experimental yield. We made X amount of copper from this experiment. Theoretical yield is always based on a calculation, oftentimes a mole problem. How much should you have made, assuming no errors and the reaction goes 100% completion? That's a lot of assumptions. So usually your experimental yield is never as high as your theoretical yield because that's assuming you've done everything perfect. But like I said, the theoretical yield is always obtained from a calculation. And more often than not, it's going to be a mole problem. How much of the starting material produces how much product? Two other things using the theoretical and the experimental yield that you are going to see quite often is percent yield and percent error. Percent yield and percent error, they will not give you these equations on the AP exam. It is expected that you guys just know how to do something like this. But to refresh your memory, percent yield is kind of like how well you did. What grade did you get? Divided by what grade you were supposed to get times 100. Experimental yield divided by theoretical yield times 100. Percent error now is taking a look at how far from the theoretical were you? How many mistakes did you make that led to hopefully a low percent error? Now, for some of you, I know you did absolute value last year. We're going to keep percent error as a positive or a negative. We're not going to take the absolute value because it gives you a little bit of information about the error. If you have a positive percent error, that means you got more than you're supposed to. So you're going to look at and analyze your procedure a little bit differently than if you got a negative percent error, meaning that you got less than you should have. So knowing if you were higher or lower is actually pretty important in analyzing the experiment and the procedure. But either way, percent error is going to be the difference, experimental minus theoretical. So if the experimental is less than what you were supposed to get, you're going to get a negative percent error. And if the experimental somehow magically is higher than what you're supposed to get, you're going to get a positive percent error. But then again, like I said, knowing if it's positive or negative, you are going to get information about, or you're going to be able to analyze a little bit differently about what you could have done wrong. All right, so that's a review of almost all of the mole unit, the stoichiometry unit that we did first year. So you got some problem sets to do for tomorrow, but we'll end it there.